Hello, I want to finish watching a post and a video. I am Pei Liu, a PhD candidate in the University of Science and Technology, Beijing. My research direction is to use data mining technology, such as machine learning, to study superalloys. My instructors are Professor Yan Su and Professor Haiyu Huang. Today, I will give you a brief introduction to the main contents of this poster in the order of the figures. When we try to make a gun-bound strengthened copper-based superalloy with potential in industrial applications, we meet a typical problem in the field of materials, that is, multi-performance optimization of material. Designing a material with multiple desired properties is a great challenge, especially in a complex material system. However, traditional experiments by trial and error or intuition are insufficient to deal with this issue. Machine learning algorithms and static inference have been recently applied to discover advanced materials and can adaptively guide the synthesis and characterization to select and optimize materials with desired properties. To effectively solve this problem, we demonstrate a materials design strategy to simultaneously optimize multiple targeted properties of multi-component copper-based superalloys via machine learning. The title of the poster is Machine Learning Assisted Design of Gun-Prime Strengthened Copper-based Superalloys with Multi-Performance Optimization. Now please look at the figure 1. In this figure, 7 properties in gun-prime strengthened copper-based superalloys, such as the microstructural stability, gun-prime surface temperature, gun-prime volume function density, processing window, failing range, and oxidation resistance were simultaneously optimized. A machine learning framework flow consisted of screen filters, global optimization algorithms, and experiment feedback is used to select the potential candidates with desired properties to experiment and characterization. In order to avoid the prediction results of the regression model trained by small data into local extrema, we adopt a global optimization algorithm called EGO to search for desired alloys with high gun-prime surface temperature. In figure 2, some machine learning models and iteration results were shown. In this A, we can see the classification model used to make classification between gun-prime phase and other phases with TCP. You can see this model has a higher OC. This means a higher classification capability of this model. And B, C, D, E. These are 4 models. These are 4 regression models built for gun-prime surface temperature, solidness, liquidness, and density. We can use these models to make some constraints to meet our design requirements, and F is the iteration results. With the experimental gun-prime surface temperature, we think after 3 rounds of iteration, the gun-prime surface do not increase significantly. Therefore, we stop this iteration. In figure 3, the multiple properties optimized for alloy 1 to 2 is shown. You can see the microstructure is very well without the precipitation of any deleterious phase, and the gun-prime surface is very high, and the oxidation resistance is good due to the formation of alumina layer. In the E and F, we show the comparison with cobalt-based superalloys and nickel-based superalloys. We can see this alloy 122 has a higher compound surface temperature compared with previously reported multi-component cobalt-based superalloys, and the multiple properties of alloy 122 could be comparable with nickel-based superalloy, such as CMSX4 and CMSX10. Even though the compound surface temperature, oxidation resistance, and fraying range are sacrificed to meet the requirements of the balance of multiple properties. In the figure 4, the microstructure characterization of alloy 122 after annealing at 1000 degrees for 50 hours. To further understand the element distribution to the gum and compound phase of the experimental alloys, element mapping is performed with high-angle annular dark field and scanning, transmission, electron microscope, nanoprobe, and acute phase comparisons were measured using APT. Compared to the partition coefficients with the reported studies in the partition change and extent of each element is consistent even though its elements contain in different cobalt-based alloys. This result of partitioning coefficients demonstrates the black box machine learning models could detect the inner partitioning mechanism of each element and provide active guidance in optimization of multiple properties and combinations, comparing the cobalt and the nickel contents in the two phases. The cobalt is the major element of the gum matrix, followed by nickel. While the contents are nearly equal in the gum-brine phase, the higher contents in the alloy expands the gum-brine two-phase field and increases the stability of the alloy, which is clearly captured by the machine learning approach. It also suggests that the future research direction is likely the design of nickel-rich cobalt-based superalloys, also known as cobalt-nickel-based superalloy, with desired multi-properties. The best performer, this alloy 122 possesses the highest compound surface temperature of 1266.5 degrees without the precipitation of any deleterious phase, a compound fraction of 74.5% after aging for 1000 hours at 1000 degrees, a density of 8.68 gram per cubic centimeter, and good high temperature oxidation resistance at 1000 degrees due to the formation of a protective alumina layer. Our approach paves a new way to rapidly design multi-component materials with desired multi-properties. So, if you are interested in this work and hope to know more details, please read the original article and contact me. Reference and my email are in the bottom right corner of the poster. Thank you for watching it. Goodbye.